Hello. For his calculator or for yours? Is that for yours? Okay, yeah, but like as a student, you're supposed to be in charge of your own batteries, right? Oh, it's just for one of his? Okay. There you go. All right. Chain rule. This is my favorite derivative rule. This is on page 14. And then once we learn our chain rule, then we can start mixing our rules together. So chain rule with product rule with quotient rule, all of those together. Again, we have to get really good at these rules because what you set up now sets you up for our next 3 units. So if you wanted to find the derivative of 3x plus 2 cubed, and we don't know the chain rule yet, our only option right now would be to multiply this out. Very fun. 3x plus 2 times 3x plus 2 times 3x plus 2. I've already got it simplified there. And then once it was simplified, you could do the derivative. Now, multiplying this all out, as we just did, looks frustrating. Not nearly as frustrating as having to do the definition of the derivative for this one, but frustrating enough that it seems to be taking a long time. And so mathematicians are like, well, maybe there's a shorter way. So they look at this answer and say, well, could I factor this answer? And the answer, I could take out a common factor of 9, and I get y prime is 9 times 3x plus 2 times 3x plus 2, and we get a bit intrigued. Hey, there was a 3x plus 2 in our original question, and our answers have 3x plus 2's in them. Maybe there's some connection. So the next step would be to do this often. You've got one example that tweaks your curiosity, that there's 3x plus 2's built into this, which almost makes us think, oh, maybe I can just bring the 3 out in front and subtract 1 from the exponent, because I got, in my answer, 3x plus 2 squared. But it doesn't quite match. There's a 9, not a 3. Okay, multiply by 3 by 3. But you go, and let's say we did a bunch of these and factored them all. This would be the next stage of trying to see if there's a pattern. So you start with 2x plus 3 cubed. Imagine expanding that out completely. It would be huge. Then after expanding it completely, you'd have to use your factor theorem and remainder theorem to try to factor it. And we get our answer, and this one seems to match, right? The 5 comes out in front, there's a 4, but then there's an extra 2. And on this one, it seems to match, but there's an extra 6x after you do everything. And the third one here seems to match that idea of our power rule happening, but then there's a whole bunch of extra stuff at the end. So our goal is to try to figure out and look at this to see if you can see the pattern. First pattern, do you see that the normal power rule seems to be happening? That the 5 is coming out in front, subtract 1 from the exponent. The 40 came out in front, subtract 1 from the exponent. The 7 came out in front, subtract 1 from the exponent. And in the last one, the 2 came out in front, and we subtracted 1 from the exponent. But the second set of brackets, where do these numbers come from, or these expressions? Have an idea? So if you take what's inside the brackets, 2x plus 3, the derivative is 2. What's inside the brackets here, the derivative would be 6x plus 0, which is just 6x. The derivative of this inside would be 4x cubed minus 1. And the derivative of this inside would be 5x to the 4. This is the chain rule. Put into words, the chain rule is for when you have one function inside of another function. So in all of these are all powers. The 2x plus 3 is inside the function that says to the exponent of 5. The 3x squared minus 7 is inside the function that is x to the 40, or a power to the 40. Okay? And when you have one function inside of another function, what we do is we do the derivative of the outside function first and keep the inside function the same. So here, I would say the outside function is the power. How do you do the power rule? Bring the number in front, subtract 1 from the exponent. So we bring the number in front, subtract 1 from the exponent, and keep the inside function the same. Then we multiply by the derivative of the inside function. What does this look like in calculus notation? There's 2 different ways that it can be written. I love this one. If y equals fu, and u is a function of x, u is equal to g of x. In other words, y is equal to f of g of x. Then the derivative is equal to the derivative of y respect to the u multiplied by the derivative of u with respect to x. And this is where a calculus formula gets confusing and where we have to go back to the wording that we looked at before. And the idea here is we take the derivative of the outside function, keep the inside the same, and then multiply by the derivative of the inside function. But the notation makes it hard to see this. It might be a little bit easier in Newton's notation rather than Leibniz's notation. Okay? G of x is the function inside of f. To find the derivative, then we do the derivative of the outside function and keep the inside the same, multiplied by the derivative of the inside function. So all we have to do is be able to manage and be able to recognize when functions are inside of other functions. So first of all, Well, I will tell you this color-coded scheme here is going to be our main method for doing all of our chain rule. I will show you how you could use Leibniz's formula to work with it, but most people will find that more time-consuming and more of a hindrance rather than being helpful. But we'll start there. So in this first example, okay, we've got y equals 3x plus 6 to the 5. No, maybe we'll start with the way that I want you to do it every single time. The way that I want you to do it every single time is go, okay, this is a chain rule because I have something inside of something else. And the something that's inside of something else has a derivative. So how do I do the chain rule? I do my outside function first and keep my inside the same. So the outside function is a power rule. Just bring the number in front, subtract 1 from the exponent. The hardest thing for students is the part where you have to keep something the same. You're doing work, you want to change everything. No, just do one step at a time, outside derivative first, keep the inside the same, then multiply by the derivative of the inside. If you wanted to simplify this, you could write it as 5 times 3, 15 in front. No problems? Straightforward. Using Leibniz's notation, you would make a substitution and call u the inside function. U equals 3x plus 6. Okay? Then that changes your original equation to be y equals u to the 5. See how that substitution did that? dy du, well, if I was finding this derivative, that's 5u to the 4. Because I have my function, y with u. That's just a simple derivative. Bring the 5 out in front, subtract 1 from the exponent. Then, du dx, I have that u is equal to 3x plus 6. So du dx would just be 3. dy dx, the derivative, is equal to dy du, 5u to the 4, multiplied by du dx, which is 3. And once you've plugged in everything into the formula, you can now substitute back what was u equal to. U was equal to 3x plus 6. And so this is how Leibniz's notation works for the formula. Some interesting things in derivatives is derivatives kind of act a little bit like fractions when they multiply. Can you imagine canceling out those du's and you have basically dy dx equals dy dx? Which makes sense. And it's weird that derivatives do that at times. But this would be how to use the formula. And I'm going to say that if you use the formula in this case, you're going to run into more issues rather than if you just learn the process directly, especially as they get more complicated. So we'll be using that sort of 3-colored thing that I had. You want to do the derivative of the outside function first, keep the inside the same, and then multiply by the derivative of the inside. Yes? You have to still use the chain rule, but this is the chain rule. You can choose if you want, if you really like this substitution, that's perfectly fine. But I'm going to say I would, over time, I think you'll like the steps as better. Okay? So first of all, recognize that we're going to need a chain rule. Do we have a function inside of another function? Somewhere, yes. I have an x squared plus x, which has a derivative, and it's inside a power of 4, which is a power rule. So we're going to have a function inside of a function. Do you also notice that you're dividing right now? If you're dividing, well, you could use your quotient rule. Quotient rule, keep the bottom the same, multiply by the derivative of the top, minus keep the top the same, multiply by the derivative of the bottom, over the bottom kept the same squared. Some of you are missing with the quotient rule. Unfortunately, at the end of the day, when I left, it was still buffering the video, so I wasn't able to put it online until this morning. So you'll have a chance to watch it tonight if you haven't seen it. The quotient rule, very much like the product rule, just a set of instructions for doing things when you're dividing. When you get to a question like this one, you have some options. You can play around with the format of the original equation, something that I would recommend. In this case, I can move the x squared plus x to my numerator with a negative exponent. Your negative exponent law lets you bring that 4 up to the top. If you do that, then you've got just a basic chain rule without having to do the quotient rule on top of it, which is what I would recommend. So now if I want to find the gradient function or the derivative, I could bring my outside function, bring the 4 out in front, subtract 1 from the exponent, then multiply by the derivative of the inside function. And we're done. If you had decided to use the quotient rule, keep the bottom the same. Multiply by the derivative of the top. The derivative of 3 would just be 0. Minus, keep the top the same. Derivative of the bottom. Sorry, I'm running out of space here. I'm going to move everything over. And the derivative of the bottom would be your chain rule. So your 4 would come out in front. Keep the inside the same. Subtract 1 from the exponent, multiply by the derivative of the inside over the bottom squared. If I square a 4, that'll become a power of 8. This is also the right answer. But our answers look really quite different. What would most likely be the answer that you would see in your textbook? The answer that you would see in your textbook would most likely look like this. They would take that negative exponent, change it back to a positive, and switch it over there in the end. Can we see that these are the same? Well, this time 0 would go away. We'd have minus 3 times 4, which would give us our minus 12. We have our 2x plus 1 up there, like this. But here I have an x squared plus x to the 3, and here I have an x squared plus x to the 8. Those would simplify to give me an x squared plus x to the 5 in my denominator. So they are the same thing. I would argue in this case, the blue seems like a lot less work. The black one requires that you know your quotient rule and the chain rule. The blue one just requires your chain rule. But you need to know how to work with negative exponents. Another chain rule, we have the 3x squared plus 7x inside of our function, which is the fifth root. In order to change this into a format we can use, a fifth root is an exponent of 1/5. And now, when I do my derivative, my outside function is the 1/5. That comes out in front. Keep the inside the same. Subtract 1 from your exponent. Multiply by the derivative. Of the inside. And this would be perfectly fine. If you checked your answer key in a textbook, it might show up like this. The negative 4/5, well, that would move that to 4/5 on the bottom. The fifths can be changed back into your fifth root, and then the 4 would stay as an exponent on the inside. I'd like you to try the next one on your own. So, first of all, you would take that exponent on the bottom, more calculus. Okay. Yeah. Yeah. No problem. And then, once you've changed it to the negative 1/2, outside function, bring that negative half in front, subtract 1 from the exponent, get negative 3/2. Then your derivative of the inside, 27x squared plus 5. Can you see that a chain rule has happened here? This is the answer. The original, well, if this 5 came out in front, there would have been a 5 originally. And then you would have multiplied by the derivative of the inside. And so this would have been the original equation. However, if Lily would like to, she could add plus 13 at the end. Why not? The derivative of 13 would be 0. It's not necessary. Again, like I mentioned before, eventually we'll be doing a plus c. Okay? Now, the way that I wrote this, would you agree that working backwards wasn't hard? Especially since I phrased it in the unit and the place that we did. Okay? How much harder would this question have been if the original was written like this? Oh my. What did I do? I multiplied the 5 into the inside brackets. Okay? What does that do? It makes this not look like the derivative of the inside anymore, which could complicate things. In fact, it complicates things more than just a little bit. This is a preview 2 units from now. Right now, we're developing the skills of our product rule, quotient rule, chain rule, power rule. We're getting really good at them. The odd time I throw one of these in, hey, can you work backwards? Working backwards is a branch of math called integration. It's all the working backwards. Everything you do in math, you learn forwards first, and then you try to work backwards. Okay? You learn adding, the next thing they say, oh, could you subtract? You learn multiplying, then they divide. You distribute with algebra, and then you have to factor. And you realize, oh, the working backwards gets more and more complicated, especially when things are simplified along the way. Okay. We've done some basic chain rules. And now we can start incorporating and building our rules together. If I rewrite this, and you'll start to recognize that you'll often rewrite things. So you can use your power rule. So anytime you have square roots, cube roots, fifth roots, take the time to change that to a fractional exponent. And we do have a function inside of another function. So we're going to have a chain rule here. But do you also notice that you have 2 things multiplied together? And with those 2 things multiplied together, it is not straightforward just to distribute. You can't distribute because you have to do exponents before you multiply. So I can't just multiply the x cubed inside. I would break order of operations. So I can't really simplify this. So I have to recognize with the green dot that I have a product. And so how do I do the derivative of a product? I need to use my product rule. What does your product rule look like? Product rule says keep one of them the same, multiply by the derivative of the other one. So I'm going to keep the x cubed the same. And then when I multiply by the derivative of my second one, that's my chain rule. So I have to say to myself, okay, I was doing my product rule, but now when I do the derivative of the second one, I have to do a chain rule. What's my chain rule? Do the derivative of the outside function, keep the inside function the same, minus 1 for my exponent, then multiply by the derivative of my inside function. And now I have to bring my head back and say, where was I in my product rule? My product rule says keep one the same, derivative of the second, then add, keep the second one the same, multiply by the derivative of the first one. And what can make calculus hard for many students is managing all of that rules inside of rules. Because all I did was the product rule, right? What does the product rule say? Keep the first one the same, derivative of the second one, plus keep the second one the same, derivative of the first one. But in the middle of doing my product rule, I was like, when I was doing the derivative of the second one, it had a chain rule. So then I had to do the chain rule in the middle of it. Sort of similar to, I don't know if you remember when we did the product rule and I had 3 things multiplied, that I had like a product rule inside of my product rule. And it's just a matter of managing that data as you're going along. The very nice thing about tests and quizzes is you could leave your answer like this. For most of the time, I will not get you to simplify. Okay? Some of the times I will, but when I get you to simplify, I'll often give you the answer and say, can you show that the answer is equal to this? And then you'd have to simplify along the way. All right. We have a function inside of another function. You have a quotient and a quotient rule and a chain rule. Option number one. So first of all, I'm going to take some time to change the 5x, the square root of 5x to 5x to the half, just so that everything is in working order. Here's option number one, dy dx. I'm going to use my quotient rule. What does the quotient rule say? Keep the bottom the same. Multiply by the derivative of the top. The top, do you see that it's a chain rule? It's a tricky chain rule because the inside seems pretty simple, but it's still a chain rule. The 1/2 would come out in front, keep the inside the same, subtract 1 from the exponent, multiply by the derivative of the inside. Minus, and now I keep the top the same, multiply by the derivative of the bottom, and the bottom is another chain rule. So I would do derivative of the outside function, 3 comes out in front, keep the inside the same, subtract 1 from the exponent, multiply by the derivative of the inside. All over the bottom squared. Oops. Oh. When I square the bottom, it comes to a power of 6. It's a minus 16x. And these are the ones that are famous as show that questions. Okay? This can be simplified using factoring, but maybe you're just not used to factoring complicated questions like this yet, but you will be. First thing that you can factor that's going to make this simpler is to recognize in your numerator you have 2 terms. This is term 1, then there's a minus sign, this is term 2. In those 2 terms, do you have a common factor? Yes. You have a 1 minus 8x squared in both of them. In fact, you have a 1 minus 8x squared twice. You have it twice here, and you have it 3 times here. If I factor that out, what is left? Well, in my first term, I would still have a 1 minus 8x squared, because I've only factored out 2 of them. But I would still have my second term here, which if I wanted to simplify a little bit would be 5 halves 5x to the negative 1/2 minus, and if I go to my second term and say, what have I factored out? I still have my 5x to the 1/2. I would still have my 3. This would be factored out, and I would still have my minus 16x. So I'm introducing square brackets here to really show the factoring. On the bottom, I still have 1 minus 8x squared to the 6. That factoring style I just did comes up a lot in your textbook work. So when you're working on your textbook and you're looking at your answer key and it's different than what you got, that step is going to save you a lot of time. Because what's going to happen next, oh, those two are going to cancel out with 2 of them on the bottom. And you would just be left with a 1 minus 8x squared to the 4 on the bottom. This might have some other simplifications, like they might change this 5x to the square root of 5x on the bottom and ask you to manipulate with that. Again, there's some really good algebra to be done in the simplification. Probably even better algebra and better skill development than actually finding the derivative. Because once you know the rules for derivatives, it's just following steps. Okay? Some people, you get to your quiz and you're like, oh no, Mr. JR didn't give us the formulas for the chain rule. Thank goodness, because we never use it anyways. But he also didn't give us the formulas for the quotient rule or the product rule. And I got to this question, and I have forgotten my quotient rule, but I remember my product rule. Can you see that you could, if you wanted to, change this to a product rule? You could rewrite this as, okay, first of all, I'm going to change that to the 1/2, and then use my negative exponent rule to make that a -3. Perfectly legal. And now, instead of dividing, I could say, put a blue dot there and say, I could use my product rule with the chain rule twice. I could keep the first one the same, multiply by the derivative of the second one. Then keep the second one the same, multiply by the derivative of the first one. Okay, I'd like you to try the next one. We have to do a little bit of work with the cube root of 1 over x. The cube root is a 1/3. A 1 over x is the same as an x to the minus 1. And then this x to the minus 1 to the 1/3, it's easy enough to put those together to give you x to the negative 1/3. If you could do that all in one step, perfect. But I did it in 2 steps here. What we do is we sort of set the table so that we can do the derivative afterwards. We have to get everything in a form that we can do the derivative before we start our derivative. If we start our derivative too soon, we're going to mess up ideas and our mathematics isn't going to work. Now, I've got a green dot there. Now it's a product rule. Product rule says keep one the same. Multiply by the derivative of the second one. This is a 4. Plus, keep the second one the same. Multiply by the derivative of the first one. And when you do the derivative of the first one, it's a chain rule. So again, we have to always bring ourselves back to what are we finding when we're finding a derivative? This, what we just found here, This is the formula for the slope of any tangent line to that original equation. That's one crazy formula for slope. Wow. In fact, the original equation is one crazy equation to begin with. This is where if you have a good graphing program, I would recommend for your phones getting Desmos. It's really easy to use and really easy to type things in. There we have our original function, something you don't, like when you look at it, it's not something you've graphed before. And then this crazy equation tells us the slope of every single tangent on that line. Whew. So with that in mind, when you look at the next example, it says find the gradient. Gradient is another word for slope. Find the slope of the tangent, and they give you some crazy equation. You need to find it specifically at x equals -4. So if you find the derivative is the formula for any slope. And then you would just have to plug in -4 to find its actual slope. Once you've got the slope, I'll have a check. Yes, you're good to go. Try the next one. You can check whether or not you had your derivative right. I did a little bit of simplifying. I'll scroll down a little bit more. Plugged in -4. Here, adding your fractions, just so I don't have to scroll down more, gives you 13/3. Tomorrow's class, I'm going to give you time to work on the chain rule, because it also makes you work on your quotient rule and work on your product rule. I'm also going to, because all of the questions I give you out of our notes are from our textbook, but sometimes it's nice to have like just a sheet of paper. You don't have to carry your textbook with you, to have in your binder. You happen to be in another class and you're like, I want to practice my derivatives. It's nice to have a sheet of paper. So this is basically it's quite big. It's sort of got 4 things together, 4 review sheets together. The chain rule is on the third part. Oh, I'll put one on there. And then we have to decide when would you be ready for a quiz on this stuff. Tomorrow? No. What's your week looking like, Wednesday or Thursday? Which one is better for you? Thursday? Okay. So that is up to the chain rule, quiz on Thursday. And a couple of the questions on your chain rule are going to be like the question on page 21, which is a show that. So on the show that question, I'll put up the answer in a bit for that as well. First of all, preliminary setup. Change the square root to an x to the half. Then you have your product rule. Keep the first one the same. Derivative of the second one. This is a tough one to see that it's a chain rule. But the derivative of the inside is -1. So you bring the 2 out in front, keep the inside the same, subtract 1 from the exponent, multiply by the derivative of the inside. Then Keep the second one the same, multiply by the derivative of the first one. So here's our derivative. Does it look at all even close to what we wanted to show? No. We have some work to do. Now, in a show that question, the answer is actually a hint. The answer is a hint because they tell you certain things need to be in your denominator, certain things need to be in your numerator. In a question like this, I would look at that denominator and say, I need a root x in my denominator. What do I have right now? Well, I have fraction exponents. My answer doesn't. It has square roots. So I might go and I might change this x to the half back to a square root. Change this x to the negative half back to a square root on the bottom. After doing that change, I see that my second fraction already has the 2 root x on the bottom. I want my entire fraction to have a 2 root x on the bottom, but I'm adding 2 different fractions. How do you add fractions? You need a common denominator. So I multiplied by 2 root x and 2 root x in the first one in green there to get that common denominator. Once I have that common denominator, I can add the tops. And at this point, there are 2 different ways you can go about this. Method number 1, multiply everything out, combine your like terms, and hopefully it factors to what the original equation was. Most students will do that. Can you see, would you maybe multiply everything out and put your like terms together? Like this would be easy to multiply, not hard. This isn't hard to square. What I want you to start to look for, which is going to help you save you time algebraically, can you see that in this term and this term, you have a common factor? That 3 minus x showed up in both of them. Instead of spending all that time multiplying it out, combining your like terms, and then having to factor, if you can see that 3 minus x is already there, you can factor it out. What are you left in your first one? Just a minus 4x. And you're left with a 3 minus x in your second one. Which, if you simplify that second one, matches up perfectly with the show that. These are the kind of show that questions you'll get on quizzes and tests. All right. The last thing, I'll just have it so that it's on the video here. The question said, after you've showed it, find out where the tangent lines are horizontal. If the tangent lines are horizontal, that means they have a slope of 0. And a slope of 0, why is this helpful the way that we've done it? The only time a fraction is equal to 0 is if your numerator is equal to 0. And it's already factored, so that happens when x is 3 and x is 3/5.